Hey, what's up everyone? Jason Turley here, back with another video, and I've just been playing around with C and just playing around with the intricacies and different things like that. I have a blog post here from a different user that I'll highlight in a second, but I've been going through this systems programming course book from the University of Illinois at Urbana-Champaign, and it has just a myriad of different topics on the C programming languages and processes and memory allocators and synchronization and so on and so forth, and all of these low-level things. And I kind of, for me, the best way to kind of learn these things is reading about them and then opening up a text editor, writing a little snippet of C, and then compiling it, and then kind of just looking at what's going on. So I have two very basic demos here, one on basic Valgrind usage and another on buffered input and output in C. These are kind of like little quirks or things you might not notice regularly, and maybe they'll cause problems in your programming and you have to debug them later, but these are very, very bare bones fundamental things when it comes with programming in this kind of language, in this kind of environment. So let's look at them both real quick. I'll open them up in Vim. I have my basic Valgrind.c, where all we're doing is allocating 100 bytes of data, and we're storing it in this integer pointer x, and then we're saying printf, please like and subscribe, which if you do enjoy these videos, please do that. It helps me out a ton. And then for our next file, I can access it in Vim by doing :next. And this is our buffered input and output. So we print a statement. It says no new line. We sleep for 2 seconds, and then we print another statement saying this is cool. Now, before I run any of these programs, I guess kind of pop quiz for yourself. What do you think these two programs will do? They might not execute the way you think they will. So let's exit out of here and let's actually compile these bad boys. So let's start with this basic Valgrind.c, and no compiler options, nothing like that. If you don't specify an object file with for GCC with TAC-O, by default, it will just give you a.out. So we can run it. Please like and subscribe. Super cool. So let's actually run this in Valgrind. So let's do Valgrind with a few different options that I grabbed here from the man page. We're going to say leak check equals full. And I don't even think I explained what Valgrind is. It is a profiler. It is a tool. It'll check for different things in regards to memory management, which is very important in these low-level languages like C or C++. It will check if you have allocated memory, but you didn't free it. It will check if there is some type of out-of-bounds write to the heap, or you're accessing data you shouldn't. It will see if you're doing double freeze. So it's very important to run this, because memory leaks on a small process like this that just runs like that, all it does is print out a statement. Who really cares if we're leaking a few bytes here and there? But if this was a web browser that we made, if this was a server that we made that multiple users interact with throughout the day, throughout the weeks and stuff like that, a small leak check or a small memory leak every time someone authenticates, for example, or accesses your web page, over time that will add up, and whatever system or resource that is, it'll start to get very slow. It might run out of resources, right? So in this small demo, it's not the end of the world. It's very easy to spot the memory leak. There is a gotcha there, but it's very easy to spot the memory leak. So we're going to say leak check equals full. And then we want leak kinds, or show leak kinds equals all for this. So let's come over here, Valgrind, leak checks equals full, and show leak kinds equals all. And don't do the mistake I did and just say a.out, because this will not actually work. We actually need to say /a.out. Well, what do you not like? Oh, leak check singular. /a.out. There we go. It prints out please like and subscribe. and saying here is your heap summary. In use at exit 100 bytes and 1 block. Total heap usage 2 Alex? Why is there 2? We only called malloc once, and then 1 free. So 100 bytes and 1 blocks are definitely lost. So we definitely lost 100 bytes. Does that make sense? So let's open up another pane, and let's go to our Valgrind input. What did I call it? Basic Valgrind. So we allocated 100 bytes, and we never called a free after it, free of X, right? So come back here. So that's why it's saying, hey, 100 bytes are lost. It hasn't been returned to the memory manager or the free store. And it actually gives us the address. Okay, this is the function we used inside of main. Leak summary, we lost 100 bytes in 1 blocks. But what is this? Why is it saying 2 Alex? So if we look at this code one more time, we call malloc, but we also call printf. So under the hood, printf does allocate some memory. It doesn't necessarily call malloc. So if I run an ltrace on a.out, we can see that it calls malloc, right? Malloc inputs, but we only see 1 malloc. But if I do an strace on a.out, I don't really love looking at it in the terminal like this. I can say strace and then tack O and give it a file name. And I'm not very creative right now. It's 12:45 in the morning. So let's just say strace.out. And now I can open this up in Vim where I actually have pretty syntax highlighting. It's easier to read. So a.out is being ran. So if I go down to the bottom, we know writes underneath the hood is actually just a system call for writes. And I do have a video explaining this in a little bit more detail from a few years ago if you're interested in that. But we see here, right above it, we see a few calls to break. So if you're familiar with malloc, we actually don't see malloc being called here, right? We see some mmaps and stuff like that. But we should see a few calls to break. This might be the data that we allocated with malloc, or is it for the write? I'm not sure. That's kind of where I kind of got hung up. I wanted to see the break and sbreak call from our malloc, as well as where is printf calling malloc, or where is printf allocating memory, because that is the function that is doing that second allocation, right? So if I do Control R for Valgrind, there's 2 Alex. So one of them is from that printf, and I was kind of going down a rabbit hole, and I found this blog that I was reading through is saying, why does printf cause a memory leak in C? I'm like, hey, this is the exact thing I'm dealing with. And it goes down and it tells us like, hey, where's the memory? This is a very simple function. All they do is call printf, and then they run it with Valgrind. They do leak check equals full, just like we did. And we see right here, there's 1 alloc and there's 1 free. So nothing is lost here. I don't know why we have data lost here. Or yes, I do. So the free is not something that we made. So printf will call free implicitly, right? Because this wasn't here before. If we wanted to fix this, we'll call free. So now our allocation of X is good, and then printf will automatically call free. So that makes sense. But I'm like, why? Like, why does it call alloc? Why is this allocating a buffer on the heap in the first place, right? Because we know the write system call doesn't do that. So if we look under the hood a little bit more, read the blog post, despite the fact that this program didn't call malloc, we see that 1024 bytes were allocated and freed. This was printf allocating and freeing the buffer that is used internally. So you might have heard of things like input IO and buffered input and stuff like that. So when you're printing messages and stuff, it won't all get sent to standard out at as soon as you call printf. It will get buffered. I don't know exactly why or all the technical terms behind it, but essentially my explanation or my reasoning or thought process is it's writing to output might be resource intensive. So it will wait until either your buffer is full, or it will essentially wait to print until it has to. So if it can group together multiple printfs, it will. If it can do any type of optimization, it will. Unless you have a new line character or call the f-flush system call. So if we keep scrolling down here, do we see them? Yeah, right here. Right here we see them, instead of doing printf, they're doing fprintf. I believe this is file printf, where you can actually give it a file descriptor here, or a file pointer, and we're giving it standard error, which, as it says later, we see here, there are no allocations. This all seems fine, but it doesn't terminate gracefully. Oh, you see right here. So we can see that there's no buffer or malloc when writing to standard error, since standard error is unbuffered. So why is this buffered? I'd have to look this up to know the exact reasoning, but I think it's something to do with what I said, some type of input and output performance. If you do know in the comments, please let me know. But unless you give it a new line character or call it f-flush, then your input might not get printed when you think it will be. So let's save out of here and let's look at our second code example. So we have printf saying no new line. We sleep for 2 seconds and then we say this is cool. So let's compile and run this. This should be 8 out. There we go. It sleeps for 2 seconds. It prints out no new line. And this is cool. All on one line because I didn't actually give it that new line character. So you might be saying, okay, but isn't that what you told it to do? It still did the printing, right? Yeah, but I wanted it to print no new line and then sleep for 2 seconds and then print out this is cool. Instead, it slept for 2 seconds and then it did my print statements. So if I want to fix this, I can either jam a new line character in here, or I could even jam one right here, or I can call f-flush on standard output. If we wanted to look at f-flush a little bit more, as always, we can open up the man page. So f-flush, flush a stream. We already have standard input output included, so this should compile just fine. For output streams, f-flush forces a write of all user space buffer data for the given output or update stream. So it's kind of like, I don't want to say like flushing a toilet, but you're essentially forcing or shoving all that data out of this stream. Don't buffer it, send it as soon as you can. So now when we compile it and rerun a.out, it prints out no new line right away. It does its sleep of 2 seconds, and then it prints out this is cool. So that's really all I wanted to showcase today. I was playing around with C, and I just wanted to showcase and share this with you guys. I thought this was a little neat. Some kind of quirks and gotchas going through Valgrind, and hey, why does printf allocate a buffer? Whereas if you do something like standard error, that does not allocate a buffer. I will go through and try to read the rest of this blog post. It seems like it's pretty well written, and I'll even leave a link to it in the description. But that's really it for this video, guys. If you know any more about printf and user space buffering, I'd love to know more. I'm going to keep reading about it, but if you guys have any input you'd like to share, as always, please leave a comment below. Take it easy, and I'll see you in the next video.